Hi, I'm Raghu. I work as a senior software engineer at Expeditors. In global supply chains, minutes of failure can cost hundreds of thousands of dollars. And most of the time, we don't hear about these failures from our monitoring tools, but we hear about them from our customers. Today, I'm going to talk about how to move from reacting to failures, predicting them, and preventing them. Modern supply chains are not just applications. They're made up of APIs, carriers, IoT devices, weather systems, warehouses, and don't fail alone. They propagate from one system to the other. A small delay becomes a missed pickup. A missed pickup becomes a missed flight becomes a customer impact. Traditional monitoring tools answers one question, what went wrong? Say for example, whenever something happens, we have these monitoring tools triggering alerts only after the performance has already declined and leaving the team responding to problems rather than preventing them. And root cause discovery during impact. Engineers must diagnose issues while customer experience disruption, increasing the pressure and extending the resolution time. Cascading failure complexity. Multiple failures occurring simultaneously obscure the original root cause and making diagnosis exponentially more difficult. External signal blindness. Critical external factors like weather events, carrier operational issues, and traffic patterns remain invisible to application level monitoring. The result would be teams spending their time firefighting incidents rather than preventing them from occurring in the first place. So what is predictive observability? Predictive observability is observability with a foresight. So we learn from the failures. Instead of waiting for the system to fail, we learn the failure behavior. So we look at the historical pattern analysis, analyzing the past incidents to identify recurring patterns and failure signatures. Real-time telemetry, continuous monitoring of system metrics, logs, and distributed traces, and integrating weather, carrier status, traffic, and other environmental factors which are outside of the applications. Proactive actions, enabling intervention hours or even days before. It's the difference between a smoke detector and a fire prevention. The goal is not better dashboards, the goal is to have fewer incidents. How should the architecture of this observability look like? There are 5 integrated layers working in concrete to transform the raw signal into actionable intelligence. Real-time observability signals. Foundation layer capturing metrics, logs, traces, and events from all system components in real. Historical pattern analysis. Time series databases and analytical engines identifying recurring patterns and trends. External intelligence integration. Weather APIs, carrier status feeds and traffic data and market indicators enrich the internal telemetry. Predictive processing engine. Machine learning models and statistical algorithms detecting anomalies and forecasting failures. Action orchestration. Automated response system triggers alerts and running remediation playbooks and coordinating human intervention. Events flow into the streams and predictive services learn from the behavior. Models forecast orchestrations enables actions. Our prediction systems are allowed to fail but are not our production systems. Event-driven architecture for prediction. Event-driven architecture provides the foundation for scalable, resilient predictive systems. By using streaming backbones like Apache Kafka and AWS Kinesis, prediction logic operates independently from the production systems. And so the 5 main things that is happening is streaming backbone, Kafka or Kinesis handling millions of events per second, continuous signal ingestion, real-time data from all system components and external services, real-time anomaly detection, immediate pattern recognition and deviation identification, decoupled prediction services, independent scaling and evolution of ML models, Prediction logic never impacts the production stability. Failed predictions are isolated incidents and not system-wide outages. Why microservices? Microservices gives you the independent scaling. Machine learning inference services scale separately from core business logic. Technology evolution. Update prediction algorithms without touching production code. Failure isolation. Prediction service failures don't cascade to operational systems. Team autonomy. Data science teams deploy models independently. And what about the distributed tracing power? Causal dependency mapping. Understand how services depend on each other. Failure propagation prediction. Forecast how issues will cascade through the system. Intervention window estimate. Calculate how much time exists before impact. Bottleneck identification. Pinpoint where failures originate. This architectural approach ensures that predictive capabilities enhance rather than compromise system reliability. Let's take a simple example, transportation network failures. Say for example, there is a severe weather event that disrupts the transportation networks, causing cascading delays across the supply chain. Traditional approaches detect these issues only after the shipments are already delayed. So the new thing what we are going to do with the predictive analysis is we take the weather forecast integration, the severe storm prediction in major transit corridors, and we look at the traffic patterns, like how much will be the delay in for during those situations. It might be usually like 4 to 6 hours, and we also analyze the carrier routes if the carrier routes are on the same path with respect to the weather forecast, and we might try to get alternate backup carriers instead of the carriers that are going to be affected. And due to this, 3 to 6 hours early, we are going to get 3 to 6 hours of early warnings, and we can reduce the delays by 90%. The second scenario is carrier API degradation. Third-party carrier APIs gradually slow down, creating subtle performance degradation that eventually cascade into system-wide failures. By the time traditional alerts fire, downstream systems are already experiencing timeouts and errors. Predictive signals. Response time trends showing consistent increase over 20 to 30 minutes. Error rate acceleration from 0.1 to 2% over short time frames. Seasonal patterns indicating peak hour degradation likelihood. Correlated slowdowns across multiple API and detection. API response time trending upwards 30 to 60 minutes before failure threshold. Prediction. ML model forecasts complete degradation within 45 minutes based on acceleration pattern. Action. Circuit breaker activated. Caching layer enabled. Backup carrier routes prepared. Outcome. Cascade prevented. User experience briefly delays instead of complete outage. The third scenario would be cold chain sensor failures. Say for example, refrigeration failures in temperature control logistics can result in hundreds of thousands of dollars in spoiled products. Traditional monitoring detects failures only after the temperature thresholds are breached, often too late to save the cargo. With the new system, first we analyze the temperature variance detection, subtle inconsistencies in cooling patterns identified. Then we rate of change analysis. Temperature drift acceleration signals compressor issues. So we check the rate of change in the temperature. Sensor consistency patterns. And with the rate of change data, we also compare with the other compressor data to find the anomalies. Cross-validation across multiple sensors reveals anomalies. So what this leads to? So this leads to predictive alert, 15 to 30 minutes warning before critical threshold, and vehicle diversion, reroute to the nearest facility for product transfer, and that will give us time to prevent the spoiling of the cargo, and loss prevention, and product is saved. Does the same ML model work for all the alerts? The answer is no. we need to have different types of alerts for different time frames. Say for example, short term is the ones which are like the live data, processing the live data, and the alerts need to be between 15 to 60 minutes. And medium term is like 1 to 6 hours, and long term maybe with the days or weeks. Coming to the short term, they capture the temporal dependencies in time series data and rapid detection of out of control processes. For use case, immediate system health degradation. And coming to the medium term, combine multiple weak predictors for robust forecasts. Handle seasonality and holiday effects in time series. Feature importance for interpretable predictions. Use case, transportation delays and API degradation. Long term. So long terms are something like we analyze both the short term and medium term and come up with a plan for the long term analysis. Say for example, with these disruptions, we are going to make changes to the capacity planning and seasonal demand shifts. Model explainability and trust. Why trust matters. Operators will not act on black box predictions, especially when those actions involve significant operational changes or resource allocation. Automation requires clear justification for every decision. In high-stakes logistics environment, a single false positive can cost thousands in unnecessary rerouting. A missed prediction can cost millions in lost product or customer penalties. So some of them are SHAP values. Quantify each feature contribution to individual predictions, showing exactly which factors drove the alert. Feature importance. Rank input signals by their predictive power across all historical incidents. Attention visualization. For neural networks, display which time windows the model focused on when making prediction. Counterfactual explanations. If the API response time has stayed below 500 milliseconds, this alert would not have fired. Operators receive actionable, credible predictions with clear reasoning, enabling confident decision-making and higher automation adoption rates. Automation decision framework. Not all predictions should trigger the same response. A risk-based framework determines when to automate, when to involve humans, and when to simply alert. Fully automated. Risk level low. Confidence required greater than 95%. Example, cache warm-up, request throttling, circuit break activation. Rational. Actions are reversible, low cost, and have proven effectiveness. Alert only. Risk level high. Confidence required less than 80%. Examples. Major infrastructure changes, vendor escalations, customer communications. Rational. High stakes decisions require full context and strategic consideration. Human in the loop. Risk level medium. Confidence required 80 to 95%. Example, carrier rerouting, inventory relocation, and scaling decisions. Rational. Significant operational impact requires human judgment and approval. This framework evolves over time as confidence improves. Actions initially require human approval can graduate to full automation as trust builds through the demonstrated accuracy. Measuring the business impact. So what's the impact of this system on the business? So the impact is we are going to avoid major incidents prevented, and we also have a cost for the system investment, and we have a cost for the annual cost avoidance, and we have the return of investment. So, and these are some of the numbers which I collected with few of the scenarios, and it clearly states that investing in these systems is going to prevent the incidents a lot, but even though there is a cost for it. And the key metrics are prevention window, hours of advance warning gained before outage impact, severity reduction, decrease in the customer-facing downtime and service degradation, percentage of predictions that don't materialize into actual incidents, and propagation of automated responses that successfully prevent outages, reduction in the time between failure initiation and alert. Coming to the conclusions and key takeaways. Predictive observability fundamentally shifts reliability engineering from reactive firefighting to preventive maintenance. By detecting failures signatures before they manifest, organizations can transform potential outages into non-events. Paradigm shift. Move from reactive incident response to proactive disruption prevention through early detection and intervention. Transform outages. Early detection converts major incidents into minor hiccups, protecting customer experience and business continuity. Scalable architecture. Event-driven systems combined with explainable ML create resilient, trustworthy prediction platforms. Proven results. Demonstrated effectiveness across logistics networks, API ecosystems, and IoT sensor deployments. Implementation path. Start small with low-risk use cases, validate prediction to build trust, then progressively automate responses. And finally, the best incident is the one that never happens. Thank you for giving me the opportunity.